In this tutorial, we will develop the idea of differentiating a function using the chain rule. To motivate the discussion of chain rule, let's work with a simpler version of it, which is called the extended power rule. So consider a function y, which is a function of gx, but this function is raised to kth power. Now, if it was just a square, then we could FOIL it, and then we could differentiate the FOILed variant of this function. But the moment this starts becoming higher than 2, a cube, fourth power, or even lower than 1 into a fraction, then differentiating this can become really messy and cumbersome. To avoid this, we'll apply what we call the extended power rule. So the extended power rule says that the derivative of gx or dy dx of this function is nothing but, we'll bring this k in the front. So we have k times g x k minus 1. Now this thing is familiar from what we did in the regular power rule, but now times g prime x. So this is the additional piece that we are working with, and that's because now we not only have x by itself, but we have g as a function of x within a function k. So we will be first treating this as just a box, and then we differentiate this with respect to x the way we would normally do using the power rule, where the k here comes in front, and then we subtract 1 from k. But now we have to work inside the box, and we differentiate this term, what we write as g prime x. So let's work with an example. Suppose our y is an apparently, a seemingly complicated function, 3x squared plus 5x to the 6th power. Dy dx of this function is nothing but, I'm going to bring 6 in front. So we have 6 times 3x squared plus 5x. And then we have 6 minus 1, which is 5. Now this whole thing times the derivative of the expression inside the parentheses, which is 6x plus 5. So this is our answer of using the extended power rule. Quite often in business and in other applications of calculus, we are dealing with cases in which a function depends on another function, which in turn depends on x. For example, consider fx to be my profits, and let's say that my profits in turn depend on my output. I call gx my output, which in turn, let's say, depends on the number of hours I'm running a machine, where x is the number of hours to run a machine. And let's say based on how many hours I run a machine for, I get the output gx, and this output in turn determines my profits. So here we see that profits is essentially linked with the number of hours I run my machines through the output produced. So this is a case where x affects g, and g in turn affects my f. So this is a case where we have a composition function. The underlying function is x, but it is linked with fx indirectly through g. So one way of rewriting this function is to write our y as a function of g, which in turn is a function of x. So this is an example of a composition function where my x affects g and g in turn affects f. So my dy dx is simply the derivative of f with respect to this whole thing. So I'll call this f prime, and I'll just leave this thing as the way it is without changing it at all, times g prime of x. Quite often, a chain rule is expressed in a different form. In this form, suppose my y is a function of some variable u, and u in turn is a function of the real underlying variable x. So what we see here is that x affects u and u in turn affects y. So we have the action in this system coming from three variables. Basically x affecting u and u in turn affecting y. So if we work with this case, then dy dx is simply the product of dy du, which is the derivative of this first piece, times du dx, which is the derivative of the second piece. So what we are saying is essentially that my x affects u, and in turn my u affects my y. So if I want to find out how my y responds to x, I will be applying a chain rule where I differentiate my y with respect to its direct variable, which is u, and then multiplied by the derivative of the direct variable that affects y with the underlying variable that affects that variable u. This example is again solidified when we work with an actual example. Suppose that cost is given by this function 5x squared plus 60 whole to the square root, which we can write as 2/1/2, and that x, which is our output, is given by this function 20t plus 40. So the chain rule says that the derivative of cost, which is actually a function of x, which in turn is a function of time with respect to time, is given by the derivative of cost with respect to x. So here we're not even worried about time. We'll differentiate cost as if it's just a function of x, and x is a standalone variable, times the derivative of x with respect to t, which, applying again this extended power rule that we have learned, this will be 1/2 times 5x squared plus 60 to negative 1/2 times the derivative of stuff inside the parentheses, which is nothing but 10x, multiplied by the derivative of x with respect to t, which will be in this case just 20. So our whole expression for dx dt is the derivative of the first thing with respect to x times the derivative of x with respect to t. Now suppose the problem says what is the rate of change of cost after 4 months of production. So in this problem, what we do is, first of all, we find out what is the x. So x at 4, and then x at 4 is given by applying it to this formula, which is simply 20 times 4 plus 40, which is 120. So now the next step involves plugging in 120 for any x we see in this expression. So dc dt at t equals to 4 is nothing but 1/2 5 120 square plus 60, and this whole is to negative square root times 10 120 for x times 20. So solving this will give us an answer for the change in costs with respect to time after 4 months, which after simplification will be $44.70 per month. The critical step here was this step where we replaced all our x values with the corresponding numerical value when time was 4 months. So once we have this step right, in which we realize that we are differentiating a function using the chain rule, which says that you differentiate your c with respect to x, that's what we did here in the top part, times the derivative of x with respect to t, which based on this being x is simply 20. And then the last step, we found the value of x at time equals to 4, because that's what the problem was, and then we plug in this value of x here to get the rate of change of cost with respect to time after 4 months of production.